By the middle of the 19th century, railway travel had made the world a much smaller place. People and goods could be transported the length and breadth of Britain at speeds that nobody could have imagined 50 years before. Then steam power was introduced to the oceans to make sea travel between the continents faster. Sadly, none of the big steam-powered liners have survived. Unlike railway engines and traction engines, they were just too big and costly to renovate and keep running once their time was up. But you can still get a feel of what a steamship was like, because there's still some of the smaller ones around. This lovely old steamboat is the SS Sir Walter Scott, built in 1899 by William Denny of Dumbarton. In them days, nearly every Scottish loch had some sort of steamship company plying on its waters to supply the houses and farms round the edges. When it was actually built, it were no great shakes, you know, it was just another steam launch on one of the Scottish lochs. But now, because it's survived, it's quite unique. It's the only one left. And one of the reasons it's survived is it doesn't do any polluting. Unlike a diesel engine that spits all sorts of stuff out into water, a steam engine doesn't. The water of Loch Katrine is the actual drinking water of Glasgow. So they can't afford to muck it up by having diesel engines like on Lake Windermere and places like that. There's nothing actually leaves the boat and goes into the lake. So let's have a look at the engine. This is it. This is what's known as a triple expansion marine engine. And it was really perfected by an American called John Elder in the late 1880s. And of course, eventually it became to be the main unit of propulsion in almost every ship they ever built. And in my opinion, it's not gone for any better. I mean, if you go in a modern ship and there's a diesel engine driving it, it's driving an oil tanker a little bigger than this, but the noise it makes is incredible. The man who looks after it isn't in lovely, tranquil surroundings like what we are down here. He's in a soundproof box with earmuffs on because of the bloody noise. And in my opinion, we've gone backwards when it comes to looking at something like this on the SS Walter Scott. 100 years old and sweet as a nut. The triple expansion engine turns a screw propeller, and it's this that powers the ship through the water. And very nice it is too. But the first steam-powered ships were propelled by paddle wheels like this. The first paddle steamers were built in the early 1800s, but like early locomotives, they had a lot of limitations. They weren't very seaworthy, and the great problem were keeping them supplied with coal because the boilers were uneconomical. And of course, when they rocked over, you got one side out the water and all sorts of terrible things happened. They were mainly used on rivers and very near the coastline. So something else had to happen. And it was one of my heroes, Isambard Kingdom Brunel, who made the breakthrough. The SS Great Britain was built by Brunel, and it was one of the outstanding engineering achievements of the Victorian age. It was the first big ocean-going ship to be constructed from iron and powered by steam. Brunel's original plan had been to build the Great Britain with paddle wheels, but he knew that paddles weren't the best form of propulsion for crossing the ocean. About this time, a new method of propelling ships was being developed, which involved having a screw propeller attached to the stern of the ship below the waterline. Brunel decided that this was a big advance on the paddle wheel, so he made changes to his design. The development of the screw propeller was one of the most important in the history of seafaring. Brunel went on to build an even bigger ship, the Great Eastern, which had paddles and a propeller, but it was the propeller that went on to rule the waves. Within 25 years of the launch of the SS Great Britain, massive advances have been made in the building of propeller-driven iron steamships, and from the middle of the 19th century onwards, all of the great transatlantic liners had propellers. All the really big steamships have gone, but there's one or two small ones survived. And this one behind me, the SS Shieldall, was built in Glasgow in 1955. And it had a rather different occupation when it was first built. It was owned by Glasgow Corporation, and they used it for delivering treated sewage out into the sea. In the summer months, they tell me, it doubles up as a passenger boat. So as well as sailing out to sea with the treated sewage, it had a load of passengers on as well. It must have been a bit whiffy. Anyway, it survived here now, and it's here in Southampton, and they do cruises. It's one of the few seen sailing round the Solent today. So I'm going to go and have a look at the engines and what it's all about inside. Hello, John. How are you doing, mate?
Hello, Fred.
All
Good
right.
to see you.
Thank you.
Yeah. Come and have a look at our boiler room.
Right. Aye. Aye.
Yeah.
Have they always been oil-fired, these boilers?
She was built as a coal-fired ship,
Yeah.
but she was converted in the shipyard before she left.
Ah, so they never had any...
They've never had any coal shoveled in.
What pressure do they run on?
It runs at 180 psi.
Yeah, that's a fair pressure, isn't it? Mind you, for compounding
Yeah.
3 times, you need to start off with a big high pressure, don't
Well,
you?
you do, yeah.
How often do you have to sweep the tubes?
Oh, we got steam soot blower.
Yeah,
Which we
blowing.
yeah, we blow
yeah.
it right out of the tubes.
Oh, I tried that, unsuccessfully.
Well, we've got the advantage that the ship can go
Yeah.
sort of out of sight of the...
Land. The big black cloud.
Yeah.
Oh. Anyway, we'll now retire to the engine room
Okay,
and
then.
look at the triple expansion engines. Aye. We could perhaps explain what a triple
Well,
expansion engine is.
The steam from the boiler comes into the high pressure cylinder first off, and the exhaust from that then goes into a medium pressure cylinder, and the exhaust from that then goes into a low pressure cylinder, and the exhaust from that then goes into a condenser where it is condensed, and it goes into the feed tank and then is pumped back in the boiler again.
Yeah. They've got to preserve as much of the clean water as they can, haven't they?
That's right.
The thing is, everything on a ship like this is run on steam, including the steering. The steering gear has got a 2-cylinder reciprocating steam engine. This alters the rudder angle through a rack and pinion arrangement working on the rudder quadrant. Rudder movements are transmitted from the ship's wheel on the bridge by hydraulic pumps, which form part of the wheel assembly.
Right.
Oh, it's
Welcome
nice
to
in
the
here,
bridge.
isn't it? Aye. Yeah. All these lovely brass electric switches,
yes.
eh? You could have that on your sideboard. How does it work, this? Like, I know it's the steering gear.
It's a hydraulic system.
Yeah. Well,
The
do
wheel
any-
connects
yeah.
to a gear wheel inside here, which
Yeah.
pushes 2 rams up and down.
Yeah,
So as
yeah.
one ram goes up, the other one goes down, and you displace fluid along the pipeline
Yeah,
to
to
the
that little
to the
engine we've just
receiver.
been looking at
That's
it.
right.
Yeah, yeah. Yeah, it's even even a check here where I noticed when you move wheel, the pressure.
Yeah,
Look
that's
at
right.
that, 200 psi already. Just that. Yeah, that's good, that, isn't it? There it is. And now it's time to get the engines turning so we can put to sea. Shieldall is fully operational and they do more than 20 cruises every year around the waters of the Solent. Back at home, I've got an interesting old book I can use to explain how these triple expansion engines work. You're on this lovely engraving of a triple expansion engine where you can, more or less self-explanatory, the steam comes in at the high pressure cylinder end and it pushes the piston up and down after the valves let it in, you know, sort of thing. And then it's exhausted into a receiver where it hangs about a bit till the valve on the intermediate cylinder opens, and then it's let through into the intermediate cylinder and it does its work there. And then it's exhausted again into another expansion chamber where waiting its turn to enter the low pressure cylinder. And then finally into down here, that big square trunking, into the condenser. What in actual fact is happening is they're using every ounce of the power of the steam. It's actually used 3 times, you know, in like a single cylinder Mammoth type thing. It's just used once and it goes up the chimney. as you might say. But in here they get, I mean, at sea they've got to get every bit of economy that they can. And of course they made quadruple expansion engines and all sorts of different variations with 3 cylinders, one on top of the other. But in a boat there's no room for that, so they've got to go long. Although the really big ships have all gone, you can still see what the huge triple expansion engines that powered them were like, because they weren't just used in ships. This is the Bratch pumping station near Wolverhampton, which has been restored by an old friend of mine, Len Crane. And the triple expansion engines in here are the sort of size that the ones on the Titanic would have been.
Anyway, come up here, Fred, and have a look. Do you want to go through there?
Yeah.
This is where it all happens.
It's almost like a ship, isn't it?
Yeah. Yeah, well, then basically it's the same engines that were in the Titanic.
Yeah, beautiful.
Yeah.
Crossing the North Atlantic.
When we first opened that regular the very first time, and it moved and turned over, a lovely feeling. Lovely feeling.
Beautiful.
You wonder what they're all for, really, but they're all doing something.
Yeah, the world's got to keep advancing on it, but in lots of ways, not for the better, you know. Instead of sitting in a bloody office with a mouse and one of them, what are they called, the computer.
Len's a real good steam man, and he's known this engine and been involved with it for nearly 60 years. But this isn't all he's got here. Parked outside, he's got this lovely steam crane. There's not many of these around, and there was no way I was going to leave without having a go on it.
We've got 3 speeds, you said.
Not synchro, man.
Yeah. Come on, old girl. There you are.
Right.
All right, a little toot.
Yep. These cranes were built to all big industrial Lancashire boilers, the length and breadth of the country.
It's on the motorway, of course.
Yeah, there's no pumps along the motorway.
The boilers would weigh up to 40 or 50 tons, and it would take a week to get from Wolverhampton to Birkenhead with such a huge load. It's a very versatile engine. A crane and a big traction engine all rolled into one. So when they've got a boiler to deliver to the docks or the shipyards, the crane will be used back at the works to lift it onto the trailer. Once you were loaded up, the traction engine would take over and tow the trailer from the works to the docks. And once it got there, the crane will be used to unload it. I really enjoyed that. But getting back to the water, the canals were still very important. Even though railway mania had gripped the country by the middle of the 19th century, the canal network was still thriving for the transportation of goods, and steam power came to the canals. This is the steam narrowboat, the President. It's 70 foot long and it's always riveted wrought iron with an elm bottom, and it was powered by a compound steam engine. The problem with the steam-driven canal boat is the fact that the machinery took up too much room. Like, you could get 25 tons on a normal horse-drawn canal boat, but one driven by steam, you lost about 12 tons of valuable cargo space. It had one good thing about it, though. It could pull 2 fully loaded canal boats called butties behind it as it went along. So I suppose in some ways, you know, it were a bit of an improvement on an horse. The boiler is coke-fired and is fed with filtered canal water by a steam pump. The original engine has been replaced and the power now comes from a simple twin-cylinder engine that came originally from a Thames launch. On the canals, the steam engine was put to a variety of other uses, especially for pumping. This is the Crofton pumping station on the Kennet and Avon Canal near Marlborough in Wiltshire. The canal which connects London to Bristol at this point is much higher than any natural source of water. And of course, every time a boat comes to cross over the summit, the water's got to be pumped up out of the river by the beam engines to enable the locks to work properly. The beam engines were installed at Crofton to make sure that the locks always had a supply of water. The locks are actually 14 feet wide and 75 feet long and contain 70,000 gallons. Every time a canal boat comes along, 70,000 gallons of water has got to be pumped out of the river at the other side of the canal. The building that houses the engines is over a total of 3 floors. And this is the top floor where, of course, the great beams are, and they're pivoted on the beam wall, which of course is the main wall of the engine house. It goes across from one side to the other and straight down into the foundations, and of course it's very strong because it's got to support all the pull and thrust of the engine. It's actually got 2 working engines in here. One of them is an 1812 Boulton & Watt, which is the oldest working beam engine in the world, still in its original building and still doing its original job. On the middle floor, you get some idea of the feeling of power. It's got an 8-foot stroke and 42-inch diameter cylinder or pistons. And of course here you get a good view of the central wall which supports all the beams, which in turn support the great cast iron beam itself. Because the actual engine house is really part of the engine. This is the ground floor where the engines control from, and at this end is the actual pumping end. Also on this floor, as well as the controls, is the boiler room, which contains 2 Lancashire boilers that run on £20 per square inch. Doesn't seem a lot, that, does it, for moving all this great mass of iron? But the secret is the actual vacuum and atmospheric pressure. By the end of the 19th century, the steam engine was being put to a wide range of uses. And when engineers were faced with the problem of how to construct a bridge over the River Thames that would allow big ocean-going vessels to continue to come upriver into the Pool of London, it was steam power that came to their aid. Because the idea they came up with was a bridge that was based on the Bascule principle of a lifting central section, and it was 2 huge steam pumping engines that provided the power to lift the bridge. This is one of a pair of compound steam engines that actually works 2 water pumps that pump up the weights in the accumulator to actually generate the energy to work the hydraulic engines that make the bridge lift up. These 2 large green iron tanks contain approximately 100 tons of iron blocks, and the steam engine works the water pumps that actually pump a column of water up underneath the 100 ton of iron. And when this valve here is opened, like I'm going to do now, the whole 100 tons comes down on the piston, compressing the water and enabling the hydraulic engine to move and work the quadrant that raises up the bridge. Bascule is actually French for seesaw, and this is the base of one of the piers that the bascules swing down into. In spite of the complexity of the system, they only took about a minute to raise to their maximum, 86 degrees. This is the actual valve that controls the pressure from the hydraulic engines, and of course I've just shut it and down's coming the bridge. Today the bascules are still operated by hydraulic power, but now they are driven by oil and electricity rather than steam. And back in the 1890s, when Tower Bridge was first opened, a revolutionary new steam engine was set to make a dramatic first appearance at an event designed to gain the maximum publicity for it. In 1897, in celebration of her Diamond Jubilee, Queen Victoria had the whole British fleet lined up at Spithead. I think there were 5 lines 6 miles long of British battleships and cruisers, witnessed by the crowned heads of Europe and the world. Into the middle of it all, an uninvited guest came speeding through, the fastest thing anybody had ever seen on water. It was the little 44-ton experimental steam turbine vessel that had been built by Charles Parsons. Here it is, the world's first steam turbine-driven ship, the Turbinia, and it's got pride of place in the centre of Newcastle's Discovery Museum. When it were actually in use, they reckon flames used to come out of the funnel, and of course Charles Parsons himself would be in here in this control room shouting instructions down to the lads in the engine room. And I mean, the thing did an unbelievable 34 knots, I think, which is nearly 40 miles an hour, and nobody had ever seen anything go so fast on the water before. The success of the Turbinia really stemmed from 2 innovations. Number 1, the steam turbine, and number 2, the slenderness of the hull. Mr. Parsons did a bit of rowing, you see, so he made it like a rowing boat on the River Cam in Cambridge. With these sort of speeds, the steam turbine could no longer be ignored. The Admiralty immediately took up a system of building destroyers with steam turbines inside them. The steam turbine is like a series of windmills inside a case, so the wind can't escape, you know, sort of the instead of it being wind, of course, it's steam, and it impinges onto all the blades of the windmill, and they're all attached to the same shaft, and of course it makes it go faster. I've got a wonderful book here that describes, I mean, when you look at a steam turbine, it don't look much at all. It's shrouded in sheet tin that covers up the great casing that contains all the works. When we've taken off the lagging, you've got to lift up the next bit, revealing the main spindle. That's what holds it all together, what it all spins round on. And then at the left-hand end here is the main steam valve, or the main delivery of the steam coming in to feed the turbine. There's the main steam pipe. Most of it's lagging to stop condensation. Then we'll sort of take the inside of the outer casing away, which reveals the actual blades, or the windmill part of it inside. There's like a slight taper in these vanes, and the reason for that is at the narrow end the high pressure comes in, and as its energy is expanded, it sort of, you know, it has less power. The vanes are a bit bigger, you see, and that's the way that, you know, it utilises all the full power of the steam. When you see one in reality, it looks ever so fragile, you know, and you think it's going round, if a bit of muck got in or something like that, it'd smash it to pieces. And these are the actual turbines in Turbinia. There's actually 3 turbines in here, like a big one in the middle and 2 smaller ones on the outsides, each of which has a prop shaft that sticks out the back end with 3 propellers on each prop shaft. That's some power, you know, when you think about it, sticking out the stern end of the ship. It's crammed a lot of machinery in an hull that's hardly 8 feet wide. It's bad enough, really, with the ship stationary, but what it must have been like doing 40 miles an hour. It must have been incredibly hot. By the 1920s, turbine-driven liners had taken over the world's shipping routes. The steam turbine virtually replaced the older reciprocating steam engine on major vessels. On the seas, the turbine-driven liner represented the high point of overseas passenger travel. Turbines meant that ships were not only bigger than they'd ever been before, but were also faster. The White Star and the French line, among others, were competing to make the biggest and best liners, but the Cunard line was the leader. Alas, you can't see many of them now, but there's still a very special one that you can look round. This ship is the world's most famous turbine-powered ship, the Royal Yacht Britannia. was built by John Brown at Clydebank. I must say, he made a wonderful job of the hull. When you look at it outside, it's perfectly smooth. And the reason for this is they're actually butt jointed, the plates of the hull. And of course, they're held in position by straps on the inside with a double row of rivets, which is a wonderful way to build a boat. And much cheaper ways, lap them over, and you could see big rows of rivets and a lap joint. But with this method, you don't see anything. It's like as though it were made of plastic.
I named the ship Britannia.
The Royal Yacht was launched in 1953 and commissioned in 1954, and between then and 1997 it ferried the Queen and the royal family around the world almost 1,000 times. Here I am in the heart of the ship, the engine room, and of course these are the turbines. The steam comes from the boiler house along this big fat pipe here into the high pressure cylinder, which is the smaller of the two black things. When the steam had done its work in the turbines and it turned the spindles round into the gearboxes, which are these two big white bits with lots of lubrication pipes on and all of that, it then in turn turned the two prop shafts to the stern end of the boat, where it turned round the propellers, and away we went. It actually took Britannia more than 1 million miles around the world with these two engines without a real major refit. This is one of the two great gearboxes that transmit the power from the turbines to the prop shafts. The prop shafts are 30 metres long and about 12 inches diameter, and turn the propellers at the other end, at the stern end of the ship, which are 10-foot diameter, and it developed 12,000 horsepower and of course propelled the ship at 21 knots. This area here were quite important. It's where the whole ship were controlled from, of course, on orders from upstairs on the bridge and the captain. But all these beautiful chromium plated wheels represented full forward gear and full backward gear, and all the pressure gauges and vacuum gauges were all important on, you know, getting it all running in the right direction. I mean, there's lots of wonderful bits about it that wouldn't normally be on an ordinary ship. I mean, steam valves have a notorious habit of dripping, and of course they've got beautiful chromium plated drip trays with little drains underneath, so no doubt it was some guy's job every morning to come round with a draining can and drain them all off. When you're done with the main steam turbines that propel the ship, you've still not done with steam round here. There's another 3 steam generating sets. You know, I'm stood here in sort of a miniature power station with 3 steam turbines that generate all the electricity for the ship. Charles Parsons had revolutionised marine propulsion with his invention of the steam turbine, but the turbine was to have an even greater impact on the provision of power for the 20th century and beyond.
Alan Titchmarsh explores a time when industry physically changed our landscape. Next on BBC Two British Isles, A Natural History.